Welcome to the 2016 Alaska Fire Presentation Series. It is being brought to you by the Alaska Natural Resource and Outdoor Education Association, or ANRO. ANRO is dedicated to promoting and implementing excellence in natural resource, outdoor, and environmental education for all Alaskans. My name is Kathy Rezebek, and I would like to introduce our speaker today, Eric Miller. Eric has worked in the area of fire ecology for 17 years, starting as a fire effects monitor in Yellowstone National Park, where he worked for 8 years. He came to the Bureau of Land Management, Alaska Fire Service, as a fire ecologist in 2008. His educational background is in botany and plant community ecology. Today, Eric will talk about prescribed burning in Alaska. Welcome, Eric.
All right, thank you. When I got asked to do this presentation, I had the impression that there wasn't a whole lot of prescribed fire done in Alaska, but through the process of putting this lecture together, I actually discovered that there's actually a pretty rich history of prescribed fire in Alaska. Before I get into prescribed fire, it's a little bit useful to understand wildfire in general. Pre-burning wildfire can be an incomprehensibly powerful natural disturbance agent. Fire is capable of spectacular destruction, but it's also capable of life-giving rejuvenation. So we see immediate destruction in the flames of a crown fire, but few of us seldom revisit a site and see plants and animals that come back afterwards. In the following years. So forests change slowly, and so we have this perception of them as static. When we see them consumed by fire, we instinctively respond to that emotionally. We actually mourn the loss of this forest that we've come to know. However, none of us have lived long enough to have seen fire sweep across the landscape hundreds of times in the past. Nor the cycles of succession where mosses and lichens, herbs, and shrubs recolonize and resprout and give way to hardwoods and shading conifers over 100 years. So this perception of fire as a powerful force has led us in the past to attempt to extinguish all fires, leading to futility in terms of expense and economics, and also unforeseen consequences such as hazard fuel buildup. Some species depend on vegetation that is only there in the years or decades following fire. Fire science and ecological understanding has led us since to use fire to our advantage, either to prevent unwanted effects or to promote rejuvenation and protection of ecosystem services and function. So the use of wildland fire to achieve desired objectives is called prescribed fire. Other names for it are planned fire and controlled burning. In this lecture, to give you a little heads up on the structure, I'm going to talk a little bit about the reasons why we burn in Alaska, and then I'll talk a little bit about the planning process, and then last I'll talk a little bit about how to actually implement a prescribed fire on the ground. So when I looked through the history of prescribed burning in Alaska, all the burns could basically be put into three categories. The first being fuel reduction, the second being habitat manipulation, and the last being for research. And some burns address more than one of these reasons or objectives. So wherever vegetation grows, dead plant parts are produced, and in humid climates, biological decomposition reduces the biomass to organic soil layers, which are quickly used by living plants. Much of the biomass is tied up in above ground living vegetation. So this is a slide from Maine, and you can see that it's a wet, humid, temperate place. And the organic materials that are shed by the overstory canopy or the trees and the shrubs are biologically reduced and recycled. And a lot of the biomass is held above ground in the plant parts. In contrast, someplace in the dry southwest like Arizona, fire weather is there all the time, and it's the fuels that are limiting. So in this, for example, ponderosa pine forest in Arizona, fire might come through here every 10 or 20 years and burn away all the organic material on the floor. In Alaska, we have something completely different. It's so cold here that biological decomposition is rare and or very slow, and fire weather is rare. So the fire frequency is long. It may take a century or more for fire to reburn a black spruce forest, for example. As a result, fuel accumulates to great depths on the ground. In one study, they measured about 85% of the total weight of plant material on the lowland black spruce site was in the forest floor. And this is an image of somewhat famous fire scientist Roger Ottmar, and he's digging into the ground, pulling out what we call a duff plug. And we're only seeing maybe half of the forest floor there, but you can see a very deep organic soil layer. As that soil accumulates, it compacts into deep layers, which become very cold and oftentimes are permanently frozen. So great amounts of fuel are always there, but in Alaska, fire weather is not. So we have a long fire cycle ecosystem. I want to talk a little bit about the canopy architecture of black spruce also, which is different from temperate regions. The low incident angle of sunlight results in trees that have vertically oriented fuel loading. So you can see they look like sticks. It's so that they can catch that low incident angle of the sunlight. And trees are adapted to retain living branches all the way to the ground. And the moisture content in the needles is also very low compared to temperate regions. So these black spruce ignite and carry fire through the canopy very easily. And a lot of times there are arboreal lichens in the branches, which are dry and dry very quickly and are very flammable. So we have a combination of great fuel accumulation on the forest floor, plus this vertically oriented spruce crown architecture. So you have a fuel complex that is conducive to crown fire. And black spruce in particular doesn't underburn like it does in other places, like in ponderosa pine forest or in interior Douglas fir forest, whose canopies are often high above the ground and less prone to crown fire. So for these reasons, prescribed fire for hazard fuel reduction in Alaska is actually fairly rare. I could find very few references to that kind of a burn. Long summer days result in long burn periods, or the warm, dry, unstable times of day when fire is able to spread. So in spruce forests like that, fuels are most often mechanically reduced or removed. This is a slide of a shear blade operation where a bulldozer comes through while the ground is still frozen and basically shears off the entire above ground forest, and it'll be burned at a time of the year when fire danger is low. And that's typically what happens with hand crews also. They'll cut down, thin the trees, make piles and burn those piles when fire danger is low. The majority of hazard fuel reduction types of burns occur in dead grass on military lands. Most prescribed fire is done right after snow melt and before green up on Department of Defense training ranges. And the idea is that they want to prevent ignitions later in the season. When they're using those training ranges, they're using tracers and bombs and rockets and hand grenades and flares and grenades and all sorts of things that will start fires. So the Alaska Fire Service and the state of Alaska burn those training ranges in the springtime. This is an image of the Small Arms Complex right across from Fort Wainwright in Alaska, or in Fairbanks. And this is the somewhat tricky burn to pull off because it's so close to Fairbanks. We have to get the winds right so that we don't smoke out the town. So the next reason is we burn is for habitat manipulation, and wildlife is pretty high up there for the reason why we want to alter habitat. Prescribed fire may be used to alter ecosystems to favor desirable plants for animals. In Alaska, fire has been used to enhance habitat for waterfowl, grouse, and moose. But fire also benefits snowshoe hares, voles, and other small mammals, which in turn feed predators such as raptors, martens, and weasels. Decadent willow stands may grow too tall for moose to access. Burning willow or aspen in the spring top kills the willow while protecting the roots. And that willow will resprout and regrow from the underground growing parts. Following burning, both the quantity and quality of the forage is improved. So fire opens up the canopy and allows sunlight to reach the ground, stimulating the organisms that decompose organic soil and making nutrients available to plants. And the ash and nutrients that are otherwise locked up in decadent vegetation become available for new growth. This is a burn we did a few years back behind Eielson Air Force Base on Fort Wainwright to improve grouse habitat. So we're burning a mixed aspen and birch forest here. Standing dead trees provide roosts for raptors and homes for cavity nesters such as woodpeckers. And fallen trees provide cover for voles, hares, and marten, shelter that is especially valuable in winter. Grouse and moose prefer early successional hardwood forests, so prescribed fire is used to top kill the aspen and birch, resulting in prolific sprouting and suckering, which provides good browse. So this is that grouse burn I mentioned in 2010, just hours before we burned it. And then 43 days later, and you can see the char on the boles of the tree, but fireweed and the birch are already resprouting. It's interesting that the birch will actually resprout from the root collar of the bole, while aspen will resprout from the entire root system. So it's a little bit slower. We'll see it in the next slide here. You can see aspen coming up everywhere. So this is exactly, almost exactly 1 year later. And you can see really nothing's been killed. The trees are still alive, it's just that they're resprouting. And if I remember right, the density of suckers was over a million an acre here, so pretty prolific regeneration. And that's what a million stems per hectare looks like. Fire has been used near Delta Junction to convert spruce forest to grasslands suitable for bison grazing. And creating and maintaining grassland helps keep bison off private and agricultural lands. The farmers don't particularly want bison in their agricultural areas. So, and then one other burn plan was in place in 2009 in the Farewell area. However, a wildfire came through the next year and did our work for us. So we got those objectives met in a wildfire, which sometimes happen. A lot of times these burn plans will remain on the books for a very long time, and then wildfire will come through and burn them before we can get the prescription window. Another habitat manipulation type of burn is to increase landscape diversity. And this is a picture from the Alphabet Hills, which were burned in 2004 to break up the decadent landscape and enhance landscape diversity in the composition of plants and animals. So in this case, it's the boundaries between the stand ages and the vegetation types, which was important. And few of the reasons might be that owls nest in old trees, but they forage in the open burn, or moose will browse in the regenerating hardwoods, but they'll rest in the cover of mature trees. So those edges are important. The last reason to burn is for research reasons, to learn about fire and fire effects. In the last 10 or 15 years, the Alaska Department of Fish and Game has been interested in burning willow and alpine areas of the Alaska range to improve moose forage. And burns of this type have not been attempted before, so they're fairly uncertain what kind of fire effects they'll get and what kind of fire behavior they'll be able to achieve. So a test burn was done, only 3/4 acre in 2008, just to see what kind of fire and behavior and effects they could get. But the overall project has not moved forward because of the tight prescription window and logistical difficulties. And one of the problems is when you burn at higher elevation, you actually need warmer and drier weather to get the right conditions. But with warmer and drier weather, you get fires elsewhere, and all of your aircraft, ground crews, and all of those firefighting resources get tied up and become unavailable, so then you can't burn. So again, it's not unusual for a burn plan to take 10 years to implement just because you're waiting for weather and logistical window to open up. Frost fire, I didn't have any images of frost fire. I couldn't find any. This was a big project that was came off the ground in 1999 and in the Caribou Poker Creek Long-Term Ecological Research Site. It's been called the most documented prescribed fire in history. Over 50 research groups participated, and they were interested in learning about emissions of greenhouse gases and other particulates, and hydrology and stream chemistry, soil carbon, water, energy pools and fluxes, permafrost, and forest succession. And all of this data was collected to feed global change models. And then in 2000, well, I guess in the early 2000s, there were big fire seasons down south, and some funding and attention was given over to how to treat fuels, hazard fuels. And those prescriptions were applied in Alaska, but there was some question as to whether they would work, because as everybody says, Alaska is different. So fire managers questioned whether those fuel treatments would work in Alaska. And some computer modeling had been done from information derived from demonstration fuel reduction projects. But a group of researchers proposed to do more. They actually ran a prescribed crown fire through experimental fuel treatment plots to see what would happen. And that was out at Nenana Ridge and on down close to the Tanana River. This is what the forest looked like beforehand, very thick lowland black spruce. And then this is what the thinning looked like afterwards. It was a nominal 8-foot bowl spacing and a 4-foot prune height. So you can see they basically took out the lower canopy of the trees and the shrubs. And so they broke up both the vertical and horizontal continuity of the canopy. And then this is sort of a encapsulated shot of the results. When the crown fire came through from the right, it basically stopped right at the edge of the fuel treatment and dropped to the ground. And then after about 250 feet or so, it actually stopped burning on the ground as well. And then, the left-hand side, I don't know if the color comes through in this video very well, but the left-hand side is all green canopies, and in the middle of the image are sort of scorched brown orange canopies, and of course there's not much canopy at all on the right-hand side where the crown fire met the fuel treatment boundary. Many people believe that it's the trees that carry fire through the forest. But if you look closely and do the science, the crown fire is overwhelmingly dependent on a surface fire. And it's for this reason that researchers and people designing these fuel treatments focus on the ground fuels and what we call the ladder fuels, the brush and lower branches of trees. And the objective here is to break the linkage between the surface fuels and the canopies. So they want to prevent that surface fire from getting up into the crowns and moving as a crown fire. This is an aerial image of that same burn, and hopefully you can see this cursor. They started burning down here in the bottom of the unit, and one crew went east and one crew went west. And you can see that the fire really didn't penetrate into the unit very well. That's because it was in the morning and the fuels were still a little bit wet. But by a little bit after lunch, a helicopter came through and dropped some ping pong balls, we call them. I'll talk a little bit about that later. But my mouse disappeared. But they actually generated a crown fire that ran north upwards through this image. And oh, there's my mouse again. Okay, this is that fuel treatment that I was showing in the other slides there. You can see that patch of green. So the crown fire came this direction, stopped at the edge of the thinning treatment, and basically went out, leaving these fuels green here. So that was a fairly interesting experiment. One part of that experiment dealt with fuel consumption and smoke emissions, and researchers measure a consumption of the surface fuels by installing pins in the ground. So prior to the burn, they stick that pin in the ground flush with the top of the surface fuel bed, and then after the fire, they come back and measure how much fuel has been burned away. By knowing the depth of burn, the bulk density of the fuel layer and the chemical properties, they're able to estimate how much heat and smoke was produced, and they can use that to make models to make predictions for other fires. Depth of burn is considered an excellent measure of fire severity in Alaska. This image here is I believe in the Boundary Fire from 2004. And that ruler is at the top of where the soil was prior to the burn. So that much soil was consumed by that fire. So very deep depth of burn. And I'd be surprised if that didn't burn all the way down to mineral soil, with the result that nothing much is resprouted. I would imagine most of these herbs have come in from seed. And that's sort of a pattern with post-fire regeneration. If the burn is light and doesn't remove much fuel, then the response is dominated by regrowth and resprouting of existing vegetation. But if the burn is deep, it favors seeding of new species from outside the burn. So the depth of burn directly affects the composition and abundance of the vegetation that grows back. One sort of fairly unique objective of at least one burn in Alaska, the 2007 Manchu burn, and was to expose and or detonate residual unexploded military ordnance. So much of Alaska was used as a training ground for the military, with operations dating back to World War II, resulting in dispersed and unaccounted munitions and explosives. Ordnance is known to be in some drainages called impact areas, but older ordnance could be just about anywhere. Burning away the vegetation allows the Army to more easily locate the unexploded ordnance. Burn crews are not allowed on the ground in these impact areas, and we certainly don't use ground cutting tools such as Pulaskis or shovels. Control is achieved through smothering tools and water. Hand ignition is limited to roads and fire lines that have been cleared for travel. And ignition in the interior is done by aircraft. So the dangers of prescribed fire and wildfire in known unexploded ordnance areas are the subject of concern and ongoing science for us. So those are the reasons to burn. I want to go a little bit into how we plan prescribed burning and some of the rationale behind it. Every prescribed fire addresses one or more resource objectives, and just some examples here: to increase the range of stand ages in the alphabet hills to improve landscape species diversity, or to create and maintain early cereal forests to reduce the chances of escaped fire, to rejuvenate decadent hardwoods to improve habitat and subsistence moose hunting opportunities. So these are just some examples, and these resource objectives come from the landowner's land or resource management plan, and they tend to be, I call them objectives, but they're really more goals. They're not very specific. They are sort of broad stroke pictures of what we want the land and resources to look like. And then every prescribed fire also has an operational objective, and that's designed to meet the resource objective. And these are more specific and directly measurable. And examples are to achieve aspen suckering densities of greater than 10,000 stems per acre within 2 growing seasons, to consume 50% of large diameter down logs, which we call 1,000-hour fuels. And we want to do that immediately post-burn. Remove 90% of the dead grass thatch and dead herbaceous fuel to reduce loading and expose the surface for military ordnance cleanup immediately post-burn. And these objectives differ a little bit from the resource objectives in that they specify a measure and a time frame in which you hope to achieve it. And sometimes the burns require both pre and post-fire measurements to know if that objective has been met. And then every prescribed fire also has an environmental and fire behavior prescription designed to achieve the operational objectives. And this allows the burn boss to know when the unit should be burned. And this sort of gets into the nitty-gritty of weather. For example, wind speeds less than 12 miles per hour, relative humidity, which is very important, between 20 and 40%, temperature 40 to 60 degrees. It also gets at the fuel moisture content that's in what we call the carrier fuels, the fuels on the ground that are going to carry that fire through your prescribed burn unit. And in this example, we want them to be between 15 and 16% moisture content. And second to last, it says burn prior to leaf out in the spring. So it actually tells you the season that you want to burn. And you might want to burn prior to leaf out because you want sunlight to get in there and dry out the surface fuels. Once the hardwoods leaf out, the understory can be fairly moist and resist fire. And then if you have done all your modeling correctly, your flame length should be somewhere between 1/2 and 2.5 feet in this example. Last, I'll get into a little bit about implementation, and I'm going to talk a little bit about control lines first. So every prescribed fire has lines of control that anchor the ignition pattern and prevent the fire from moving outside the project area. In this example in the slide, it's a road, and once the ignition occurs, the right-hand side will be referred to as the black because it's shortly to be black, and then the other side of the road is the green, which we hope will stay green. This is old logging road, can be used as a fire line, and can also use rivers and snowbanks. And it's hard to even see here, but there's a hand line on the lower right-hand side, and it's really hard to see, but it's enough to keep the fire within the burn boundary here in this image. Reinforced by firefighters who are using beaters and smothering tools and some water from bladder bags. And that's called wet line, when you put water down and burn off with water. These the fire line can be reinforced by a hose lay. In this case, there's a Mark III pump in a pond, and the unit is completely surrounded by hoses, and the firefighter in the middle there is using that hose to douse down areas that are of concern. The important thing in all of prescribed burning is to keep the black in the black and the green in the green. This image I found on the internet, and I egregiously used it. It's from the Nature Conservancy, and I used it because it's a great illustration of how a prescribed burn is done. And it looks like these, there are two crews on a prescribed burn. There are the igniters, and then there are the holders. And the igniters, looks like my mouse is gone, have drip torches or other incendiary devices. And it looks like in this image that they have burned on the upwind side. The wind is heading right to left in this image. So they've burned off the river first so that they're getting backing flames going through the unit. And you can see that those flames are tilted to the left. And those flames are moving much more slowly than they would if they had burned on the headwind side of that unit. If they had started fire on the right, those flames could have moved right through the unit, spotted over the river, and then it'd be off. So firefighters generally start their ignitions on the most advantageous side of the unit. And generally that's they want to burn into the wind. And they'll burn generally from the top of a hill down to the bottom. Because again, they want to keep those flames small and slowly moving. So the igniting crew has gone around this unit and they've brought fire completely around it. And then a second igniter is coming down the right-hand side and setting head fire. And then if everything goes according to plan, the unit will be black. Drip torches are the tool of choice. They are filled with a mixture of what we call drip mix, which is a combination of 3 parts diesel to 1 part gasoline. Diesel itself doesn't ignite very well, and gasoline is explosive, but when you mix them at the right ratio, they burn really nicely. And you can see a wick on the end of those drip torches, and that gets ignited, and then the fuel flows over that wick, catches fire, and is dropped on the ground, and it burns for a minute or two. So you can drip that fuel out onto the ground to start fires, or you can lay a very big long line of fire. It's a very, very handy tool for prescribed fire. In a bigger burn, which maybe thousands of acres, the center of the fire is generally ignited by helicopter. And we're looking at a plastic sphere dispensing machine. And you can see in the hopper, there's a whole bunch of what look like ping pong balls. And those ping pong balls are filled with a chemical, a dry chemical. And when they're dropped from the helicopter, they're briefly stopped and injected with ethylene glycol, which reacts with that dry chemical. And in a few minutes, once that ping pong ball hits the ground, it starts on fire. And you can see in this image here, the helicopter has dropped, looks like 3 ping pong balls a few minutes ago, and now they're starting to ignite and carry fire. So helicopter is a great way to ignite the middle of a burn if you want to cover some territory fast. And then this last image here shows a phenomenon that we try to take advantage of, and you can see that hand ignition has been brought down both sides of the unit, and then the center of the unit has been fired, and you can see great big flames in the middle. And that's because as that middle of that fire burns, it generates its own wind. And that wind does several things. One, it kicks up the fire behavior in the middle of the unit, so it's going to burn a lot hotter in the middle of the unit than it will around the edges. And the second thing it does is suck all that smoke up into a column. So in essence, it ejects it high as, high as you can get it, really. And that serves, one, to get the smoke up so that it will disperse. And then 2, it tends to suck embers and spots and firebrands in towards the center of the unit rather than blowing them out into the green. So that's sort of the pattern, is to bring fire around the unit and then fire out the middle, and then just suck everything right into the middle of that unit. And then my last slide here is about addresses cooperation. Fire management is a very complex endeavor and requires discipline, efficiency, and training much more than any individual agency can provide for itself. And this is especially so in Alaska with a small population relative to the size of its wildlands. So it's common for burn plan preparation and implementation to be done by staff from many agencies at the federal, state, and local levels. Firefighters on the ground commonly include employees of the state of Alaska, the National Park Service, Fish and Wildlife Service, Bureau of Land Management, U.S. Forest Service, Native corporations, structural firefighters, contractors, the Army, just to name a few. The roles that the different firefighters assume are clearly defined and are the same from burn to burn. So it's a plug-and-play operation. Every position on a prescribed fire can be filled by a number of people trained to do that role, and the roles are the same between prescribed and wildfire. So a prescribed fire minimally have a burn boss, a firing boss, a holding boss, a monitor, and firefighters. And more complex burns will include aircraft, engines, water tenders, 20-person hand crews, and again, the list goes on. It's more than any one agency can supply at any given time. So the fire community is very cooperative and coordinated. So that concludes my talk on prescribed fire. Thank you for attending.